So I was given this title, no Evidence for Neutrino Oscillations, and of course almost everyone in this audience realizes that there are neutrino oscillations. So how did we get this? Well, where there isn't any. You know, you can do an experiment that is either so poor or, just is looking at something that somebody else thought was an oscillation that you really end up not seeing anything. So I first, here's kind of an outline. So sort of the earliest encounter, a thing I call the letter. It's crucial. It's big in Stuart and mine life. There's E645, an experiment that was carried out at Los Alamos. Oscillatory decay rates. I won't say anything, I think, about reactor neutrinos, and sort of close. So the earliest contact was when Stuart finished that wonderful thesis that that we've heard so much about, and came out to Princeton as an instructor. I don't know if you've picked him out yet, but there he is. Showing up, and I'm in the picture somewhere. That's me. I think there's Jim Peebles, Dave Wilkinson right next to me, and then a very prestigious lineup of people in front. Shamefully, many of us young experimentalists at Princeton didn't really appreciate Stuart's thesis, because we had already believed in quantum mechanics, and what's the big deal? However, both professors Wigner and Wheeler were very, very impressed and spent much time talking to Stuart about those experiments. We worked. I don't think while Stuart was at Princeton that we actually did any science together. We became good friends. Both Joyce and he and myself and my wife enjoyed their company a great deal. And as you heard yesterday, Stuart was a motorcyclist, a glider pilot, and a sailor. At Princeton, we did some gliding. That Jean may tell us a little bit about at supper. But that was what happened. I moved off to Argonne in '76, and Stuart a few years later went out to Stanford. Now, after his stint at Stanford, he was looking for a position, and we were very interested, John Schiffer and I, in attracting him to Argonne. And I had made a verbal promise to Stuart as to how he would be treated if he came to Argonne, but he was not satisfied with the verbal account. He wanted it in writing. And this was a time before HR was very intrusive in the hiring of people. So you'll notice that you'll notice the Hemingway-like prose, and well, I would say I more or less honored that, and I would say that this was characteristic of our relationship. It was close. Oh yes. Oh no. This is the copy hung in his office. It might still be there. I don't know. But I thank Joyce for this, for the copy of this. But this is the kind of relationship that we had. So now let's get on to a little bit of science, even if it's not all that great. So the first experiment that we got involved in was an experiment. It ended up publishing in 1993, but we started it in around 1982 or 3, just after Stuart arrived. It has many of the usual suspects. Stuart was the lead author. The paper was much better written than it deserved. Brian was there, Jim Napolitano, Bob McEwen, Kevin Lesko, myself, and then some high-energy interlopers. The experiment was really pretty simple. It involved creating pions with an 800 MeV beam at Los Alamos. The pi minuses would be observed, and you were left with pi pluses, which were decayed into a muon neutrino. The muon then subsequently decayed into a positron, an electron neutrino, and a muon antineutrino. So, and the spectrum of these particles is well known. Shown there, the maximum energy of that decay is 52 MeV. And the experiment was to look at the oscillations of that mu minus particle into, the muon antineutrino into the electron antineutrino as it flew over to our detector. And the detector was to detect the decay by the electron antineutrino interacting with a proton, giving you a positron and a neutron. So conceptually pretty straightforward. It was, by the standards that Stuart and I both operated at the time, was big for what we were typically used to, as for the most part we were involved in much smaller experiments. So the actual setup of the experiment had the beam stop over here and some 30 meters away through a lot of dirt and overburden shielding. We were to carry out this experiment, and the oscillation was to have occurred in that intervening 33 meters. This was a time when we didn't really know a great deal about neutrino oscillations, especially of muons. We certainly knew that the solar neutrinos had evidence of oscillatory behavior, but we didn't know what the mass scale might be for mu to E conversion at the time. So the detector was designed by a group largely from Ohio State University. It was a combination of scintillator panels, some gas counters that you could track the electron through, and here's the way the particular lineup of scintillator tanks looked. And one expected maybe to see something like one event per day in this detector device. And of course, the thing you really had to worry about in this case, in this experiment, were cosmic ray muons, which rained on the detector at the rate of 3,000 per second. And you would get the order of 15 triggers per second in this detector from that particular case where the muon stopped in the detector, emitted this electron, and of course that electron would look just like the signal that you needed to use to determine the oscillation. So you really had to get rid of those cosmic ray neutrons, and so you had to build a shield around that to shield against those muons. And the idea of, and this gives you an idea of just how well you had to do that shielding in order. This is, I think, the order of one cosmic ray background event per day coming in order to get a good limit on mixing angle for the oscillation probability of the muon antineutrino into an electron antineutrino. The one really good feature of this whole thing was the way the shield was designed. And it really was due to Stuart and Jim Napolitano that came up with this idea. In order that you have a trigger rate that's not too high, that is, you just are not too susceptible to general background radiation, but made sure that what was coming through your shield was a muon detector. They made a detector that was about 6 inches thick with liquid scintillator in it, and this was the test stand that they used. See, it was a square 1.5 meters by 1.5 meters, 4 phototubes stuck in it, and this is how they studied it. And these were paddles that you could determine that there was a muon actually going through those particular areas. One of the things that they discovered was that white paint was a lot better than just using shiny metal. This is signal that you saw when you used white paint with the cosmic ray passing through position 1. You see a nice signal when you're just looking at all the things in general. You really got a pretty good signal from just a cosmic ray passing anyway through. If it was just simply polished steel on the inside, it really was nowhere near as good. So painting everything white in the shield was a really important step. And this shows that rather than just depending on pulse height, you asked that you had coincidence between 2, 3, or 4 tubes, or if you're just selecting out of 3, between 2 and 3. So you see, it really was quite a robust setup that was really sensitive to passing cosmic rays, and you didn't have to accept too much background. That was important because every time you saw something in the shield, you wanted to turn off the detector for that time so that it didn't trigger, and you could not allow that rate to become excessive. Now, I think one of the interesting things that happened, this is with regard to the detector, when they were testing those modules, I'll not go back to the previous slide, testing the modules that held the liquid scintillator in the detector, we were asking them how it was going, and they said, well, we really see really good signals in those detectors, but after half an hour, they break and fall apart. And it turned out that there was just a serious misconception in how they were designed because there was curvature in them, and the pseudocumene in the mineral oil that was there just basically ate into the crazing that occurred at the curvature and ended up breaking the detector. So we had to find a new way to actually make those detectors, and a suitable solution was come by. So this is the way the shield ended up looking. It was designed by Ken Coover, an engineer at Argonne. This is the outer part of it. Really a very nice design. I'm sure Stuart and Jim had a big hand in helping Ken design it. This is a picture at the back of the detector, myself and Stuart. I think you probably can tell us apart. That's me. That's Stuart. Another shot looking into the tunnel in which the detector was placed. You can see this was a relatively large experiment. Closing in on that figure, you can see the person standing there in the middle really is Stuart. Here is a picture of what that shield actually looked like. Kevin Lesko on up there. Yeah. Okay. And here is Bob McEwen and Jim Napolitano. Again, inside the tunnel, looking at a part of the shield. Well, after several years' work, This, unfortunately, was the exclusion result that we had. That was, it was possible that there could be neutrino oscillations anywhere outside that bound. And you can see that there were several experiments that really did a much better job. But I think that, for the most part, the reason that it was not a very good job was that the detector was really remarkably inefficient. It was light. It was only about 20 tons because so much of it was taken up with gaseous tracker, and it required forward or backward going electrons, and at those energies, the electron distribution is nearly isotropic. However, the VTOL is absolutely terrific. Online, since it only passed 1 in 10,000 muons without giving you a signal. And when you analyzed it online, that inefficiency grew to about 1 over 3 in 10 million muons. So it was really the state-of-the-art shield, and in fact was so successful as a shield that when a subsequent experiment done at at Los Alamos called LSND, of here, which managed to increase the mass of the detector by about a factor of 8 and the efficiency in triggering by a factor of 3. So it was a 25 times more efficient detector of neutrinos, and found an interesting result, sometimes called sterile neutrinos. And I only wish that Stuart had the time and was provided with the resources to prove one way or another whether those things really exist, because it's still a rather open question with believers and non-believers, but nobody with very firm evidence one way or the other. Now, GSI provided Stuart with another opportunity to go looking for an interesting effect. And in 2008, there was a report of an oscillatory decay curve for the electron capture decay of hydrogen-like promethium and praseodymium and promethium. So these things were hydrogen-like. They were stripped down to the point where there was just a single, and they're trapped in a storage ring. And the decay in both cases took place by the capture of that orbital electron. It's a very fancy experiment in which, again, it was a unique facility for generating this kind of an experiment. From their UNILAC, the heavy ion accelerator that John spoke about, there was a ring in which you could accelerate them to even higher energy, and these I think it's 100 samarium 152 was accelerated to extremely high energy, brought into a ring, and finally injected into a very sensitive electron storage ring at the GSI. The detector of the circulating praseodymium and promethium was done as a pickup, some Schottky pickup, picked up those the sense of that very highly charged ion, and could record the time that it took for it to fly around the ring to exquisite precision. So here's a picture of the ring. The ion is injected here. Electron cooling brings the momentum fluctuations or the temperature of that beam down to the point that variation in the velocities are effectively zero. The ions traverse this ring, and of course, the things that are slightly heavier, in this case because everything is extremely relativistic in the ring, these just take a longer time than the lighter ion would take in traversing that ring. Just to give you an idea of how exquisite the resolution of that ring is, this is the ground state of samarium 143. This peak here, looking at basically the frequency or time, and a state at a metastable state that's just 754 kilovolts above the ground state is displaced by that amount. The mass of these particles is the order of 140 GeV, so that separation is quite remarkable. What they had seen was the injected particles, basically the order of one at a time. This is promethium initially in the ring. It undergoes electron capture after some time in the ring and starts showing up as cesium 142. In the case here, there's 2 ions of promethium circulating. After a certain time, one of them turns into neodymium. And this is the signal that you're seeing at the Schottky counter. So it certainly looked like a device in which you could certainly measure things very well. And the amazing result that they were seeing was that the decay, in this case promethium, showed this clear oscillatory behavior. Very, very surprising. This is a frequency spectrum, and I think it ends up with showing a period that's the order of a few seconds. In fact, the next thing, they fit the decay to an expected exponential decay, and then and some amplitude for the oscillation, a frequency at which it occurs. And of course, the thing that's really surprising about this is that it has to have a phase that's fixed. And you would certainly puzzle, where did that phase come from and when did it occur in this whole process? I mean, at some level, exponential decay is the idea of, at some level, maximum ignorance. All that you have to know is how many of the decaying species are present, and it exhibits a half-life. Nothing else is required, and you get exponential decay. So this was indeed surprising. Here are the amplitudes that are seen. For promethium, it was an amplitude of 0.18 out here. The frequency is the order of a second in both cases, almost. And the amplitude here is 0.23 for promethium decay. So an extremely perplexing and surprising result. Now, you might say, well, what's this got to do with neutrino oscillations? Well, this is what happens. The promethium is going around with this electron, captures the electron, but a neutrino is emitted. So that's what it's got to do with neutrinos. At least there's a neutrino involved. You can say that much. Now, that 7-second period, implies an extraordinarily small energy scale. In fact, if you look at it and figure out what that delta E is using the uncertainty principle, it's the order of 10 to the minus 16 electron volts. That's an extraordinarily small energy. One doesn't know many physical processes that occur on that energy scale. However, if you look at what is the scale set by electron-neutrino oscillations, There, the delta E can be given by the mass splitting of the two neutrino masses divided by twice the mass of promethium. You work out those numbers, and admittedly, it's certainly not the same, but people thought, good Lord, the fact that it's in the same range means it must mean something. They're related some way. So, controversy goes on. So plot as a function of time, yays and nays. I would say, if you sort of looked at the authors, you might feel that the heaviest hitters were on the nay side. But, that's the kind of prejudice that we physicists have to be careful of. And Stuart was bound to get involved in this. And so he set out for a search for oscillations this is a published paper in Physics Letters, of the electron capture decay of promethium-142 with his collaborators. I'm sure Paul Vetter had a really large role to play in this particular experiment. So I'll describe how they ended up getting a sample of promethium embedded in a very thin foil of aluminum, and then looking at the decay in a germanium detector. And what they're looking at, this is when they're just basically counting background, and this is the counting that goes on when they're looking at the actual decay of the promethium-142 in the aluminum foil, and they see these capture lines. Now, the promethium in this case, of course, is not fully stripped of its electrons. It has all of them around them, but it was the best one could do, and this is roughly the decay that they saw. Just to show you how that experiment was carried out, it was done right here at Berkeley. I'm sure a lot of scrounging went on in putting it together. There is the 88-inch cyclotron. It had a very robust beam of sodium 23 incident on a foil of tin 124, and a whole spray of stuff comes out of that target. But in the Berkeley gas-filled spectrometer, you can actually use the idea of the equilibrium charge of the ions as they go through, and you can set some slits and select promethium 142. And so that was what was done. They then shut off the beam and look at the decay of the stuff in the foil in that detector. And this is a schematic idea of just to show you all the electrons were present, and of course what you were doing were, for the most part, capturing them out of that S orbit. So this is their result. Sort of a giveaway here. Here's what they observed. There is the amplitude of the oscillation you would have expected if the number seen at GSI was correct. A look for frequency. They did not see anything out at the characteristic period that GSI reported. If you took the formula that was used at GSI, assume there was no oscillation, and then obviously no frequency or phase angle, the chi-square that you got was something like 618 over 594 degrees of freedom. If you made a best fit to those various parameters, you can certainly see that the amplitude here was way below the 0.28 claimed, 0.23 claimed in in the GSI paper. And the chi-square just improves minimally over what it was, assuming that there was nothing. So, no oscillation. So Stuart really measured nothing, I think, when there was nothing there to be measured. And that's better than a lot of us do. It really was quite a feat. I think in every case he got things right. He wrote up the results in an absolutely great way. He was an enormously good friend. I like to think of him as one of the closest friends that I had in my physics career. And it was a joy working with him. I should share with you, in those two earlier phases, both at Princeton and Argonne, I was what you might call his boss. And that's not an easy job. But as a friend and colleague, he's absolutely terrific. Thank you very much.